Hello and welcome to Deep Learning Leaders. My name is Eric Landau and I'm the CEO and co-founder of Encord, the data development platform for AI teams. I'm happy to be joined today by Kit Merker, the CEO of Plainsight Technologies. Plainsight is the enterprise vision data company and brings vision capabilities to watch and analyze events in the real world and generate structured data for analytics and reporting. They work in a variety of verticals and enterprise use cases, including manufacturing, retail, food service, theft, and more. Thank you for joining me today, Kit.
Great to see you, Eric. How are you?
Nice to see you as well. I'm doing well. So I wanted to actually start with a bit about the history of Plainsight, because you came in a little bit later from the founding of the company, which I'm curious also, how you ended up joining the company. But can you describe a little about when Plainsight started and how the company trajectory has looked over the last few years?
Yeah, I joined Plainsight almost 18 months ago now, and really the idea was to take what had been a professional services company around vision applications and turn that into a software infrastructure company to support vision workloads. That was really the big idea of the transition that we were trying to create. Plainsight had been around in a variety of forms for actually many years and had started its trajectory focused on telecom solutions, then had moved into IoT, and then vision as a capability later on. And so I think the company had really strong engineering talent and a lot of deep understanding of how to build bespoke solutions for customers. The challenge that we're seeing, especially as AI is becoming more and more prevalent and the market is evolving, is we have to drive down the cost of adoption for computer vision. And so my background prior to this, I really am not an AI vision guy, really. I mean, I have obviously dabbled in it throughout the years, but my background primarily in developer tools, cloud infrastructure, and building really, really scalable software systems. And so my CTO, Andrew Smith, who, his background at Amazon, Google, Microsoft, we both came at this computer vision problem thinking about workloads and cloud workloads in particular, and thought, well, how can we reimagine what we see in computer vision as this very scalable way of connecting cameras and video and images and create data pipelines and data services that then emit really actionable data for enterprises. And so the idea of jokingly, but not really, is like cameras to spreadsheets, right? Like how do we take all these cameras in the world and generate data for the massive spreadsheets in the world? And when I say spreadsheets, I mean ERP systems like SAP. These are the joke is that all enterprise software is just a spreadsheet in disguise, right? Yeah. So the idea is how can we feed all these camera systems from enterprises, and businesses that are producing things in the real world and turn that into data that's useful as they sort of digitally model their business. And so this is the trajectory we've been on recently. We used to have, Plainsight historically had its own annotation platform, for example, which we disbanded in favor of Encord. The other big interesting thing is, I think in computer vision, and you've seen this, I'm sure, as well, there's a lot of focus on industry vertical use cases and sort of going deep on use cases. How can we build reusable infrastructure, right, that really solves the vision workload problem, and this vision workload that applies to many, many different scenes and scenarios, and then allow other companies that have much deeper expertise to do that and bring these solutions to market by adding vision to their capabilities. And that has been, for us, I think, actually quite a differentiated approach. We are able to build abstractions that I think serve many, many verticals.
Yeah, indeed. No, that's super interesting. I have a ton of questions. So what do you think the primary bottleneck actually is for these vision workloads? Is it the cost? Is it the scalability? Is it getting the accuracy of the models to these production level use cases? Is it some other component, some kind of mixture of things? What do you find is the thing holding it back the most at the moment?
Yeah, I do think that cost is a big factor. I think there's a big gulf in expectations. I think one of the dirty secrets of the AI industry generally, but in computer vision in particular, is that the end customers have been trained by movies and demos to believe that it's magical and it just works, and there's really no hard work in it. So all the things that go into fundamentally what we're what companies are trying to do with these automated vision systems. If you're doing it for business, forget consumer for a second, but if you're doing it for business, fundamentally you're trying to replace labor. People are expensive and lazy and get sick and go on vacation and all these other, all these other things, but they have a base capability of vision, and you can get people to do these basic vision tasks. I think that is one of the big things. So the expectations, the cost. Data is a huge problem, as you know, getting data accuracy. I mean, today, the actual model training step is not rocket science, so to speak. It really is a garbage in, garbage out issue to a large extent. Yeah. We have pretty predictable ways of creating models. The issue, I think, is more on the issue of how do we get the data into a state where the model training will be predictably good, right? It has to do with the surrounding data management and video management around vision, and this is, I think, particular to vision, very different than text. I think one of the reasons why ChatGPT has made the advantage it has is that you can fit like the entire works of Shakespeare on like a tiny little kind of little thing.
Yeah.
Video is optimized for human consumption. The information, the actual information density of video is quite low relative to what is transported. And so one of the things I think, which is a technical insight for us, is that if we can tame that sort of signal to noise ratio on video, then that can have a direct impact on training, data quality, content delivery. So one of the ways I've described Plainsight is that we're building Netflix for robots. If you think about like video streaming infrastructure for humans, it has a certain characteristic. When you think about that video streaming infrastructure for automation, for agents, for LLMs, for AI systems, you can really design it differently. And you can get rid of a lot of the redundancy, information compression, semantic compression, et cetera, because frankly, the robot is not experiencing watching a movie or watching a streaming video. They're trying to find the data, which of course is incredibly small.
Okay, so that's super interesting. So maybe just drilling down a bit, if cost is one of the key bottlenecks, is it the cost of processing the density of that data? Or is it costs of collecting the data in the first place, the cost of doing the annotation or other types of curation workflows? What is the principal cost that dominates the others, if any?
Yeah, so I think it boils down to a couple things. One of the big ones I think is about GPUs, and in particular GPUs at the edge. Okay, I think that the traditional approach to computer vision goes a little something like this, right? So if somebody has a computer vision problem, they see a demo of it working on, one short video that's been trained on some small amount of data, and it looks pretty good. We'll leave aside the biases of, test versus train split of the data and like how accurate those things are out of the box. But somebody sees that, and then they go, okay, cool. I have 5,000 locations. So let's go roll that out. And you say, okay, so that's going to be 5,000 cameras. And, I have 2 or 3 models per camera. And then I got to buy a GPU per model per camera. And then all of a sudden it's, it's an astronomical bill, like in the, tens or hundreds of millions of dollars. And the project usually gets canceled at that point. And people go, what the heck, right? And this is partially because that scale doesn't scale down, right? When you slim it down to like, one model, one GPU, whatever, it sounds kind of reasonable and you can get started. But once you start to scale out, so there has to be some ability, I believe, to condense that workload onto GPUs that are shared, right? And so that is a scaling factor of cost that I think is a big issue, and one that doesn't come until post POC, right? The way we address that is by we push a lot of cheap algorithms to the edge that then drive GPU in the cloud, and we have some techniques we use for that. But that is really the idea, is that we want to put almost no requirement for GPUs at the edge and really move that into cloud. That way we can shard work and we can carpool on it, et cetera. So that's one for sure. The other one, to your point about the model training, et cetera, this is one that not only has a labor cost, but also has a time cost. And part of how we're thinking about this problem is that training should be continuous, and the annotation process should be continuous. And so that means that when data is coming in through these cameras, we actually want to feed it both into the inference pipeline to generate what we call subject data, which is basically the data about the system that we're observing. But we have a secondary use of that data, which is the exhaust of that data goes into the annotation pipeline and is then used to train sort of V-next of the model. Yep. And when you have this continuous process, sure, you got to bootstrap it. But once you get past bootstrapping, you can start to pre-annotate that data using sort of yesterday's model, right? You can start to use other techniques, that I don't fully understand, out of distribution detection. And there's other kind of machine learning techniques and data management techniques that can be used to flag outliers and exceptions, and then feed that into a sort of human in the loop process that then feeds into the next version of the model. So that's, I think, an important part too. I'd like to tell customers that accuracy is a journey, right? You're going to start off with some level of accuracy, and then the goal is that we're going to increase that over time. But you don't want to wait until you get perfect accuracy to start using the system. You want to iterate with it and find ways to make it adjacent to your existing manual workflow or whatever it is you're currently doing. Put this off to the side until you get to a level where you can trust it, and then kind of build that continuously. That's one way of shortening the time and also the cost associated with the training. And then there's some other costs around the sort of engineering and the toil of building these systems. But then the question is but how are we going to scale it up to many, many, many replicas, which is what enterprises need in order for it to work. That transition to me right now, I see in the market is incredibly expensive. And so I think there's an opportunity for us to really automate that process, to say, what, we're going to build scale agnostic tooling, which is kind of a Google mentality, right? We're going to build, the tooling will be scale agnostic, whether you're working with a small amount of data or a large amount of data. The way you're going to think about that in terms of abstractions and design, et cetera, are going to be the same. That's where a lot of the IP is coming in for us. Like those are the tools we're building, is really about, frankly, that transition. Because we're not reinventing how to build computer vision. What we're trying to reinvent is how to take computer vision from a small scale to a large scale in a cost-effective and reliable way. Yeah.
Okay, so the three kind of mitigators of what you said. One is good heuristics or compression techniques at the edge to minimize the amount of data that actually goes to the cloud. Yes. The second is this, what we see as the gold standard, this kind of continuous annotation and training loop with humans in the loop and labeling with your previous models, outlier detection, all the stuff which the best teams are doing. And the third is coming up with this scale agnostic system that has the right abstractions in place to kind of mitigate the transition of the POC stage to the production stage. So there's like a few different innovations happening in parallel, maybe starting with the edge compression, right? And this goes a bit back to your point of the signal to noise, and vision is a very redundant form of data. Is the kind of compression layer deployed in these algorithms that you put at the edge, or is that another component that comes later downstream? And if so, like how do you at the edge determine like which events, which frames, like which pieces of data are actually interesting enough to actually put into the cloud in the first place? Yeah.
So we have a number of different tools that use what I would call traditional computer vision techniques that can run on a more constrained scene, a more constrained environment. They're more constrained in what they can adapt to. AI is really great at kind of general purpose, just sort of point the model at something and it works. So imagine you have a smaller set of activities that you can detect, right? But that means it's also computationally simpler. And that could mean using inputs. If you just think about what we really have with the video stream, is it's a 2x2 matrix of RGB values, right? It's like that's what we really have, and that's changing over time. But if you think about it in terms of frames, you really just have like this matrix of numbers that represent the colors in the frame. There's actually no motion. There's actually no lighting or whatever. It's all just RGB values. So if you kind of think about two vectors of compression, regions of interest and frames of interest, right? You think about those questions like, well, how am I going to determine the region of interest? And then within that, how am I going to determine the frames of interest? So you can look at the color data coming off of these pixels within different regions and different frames and start to build an event model of the video, right? And so then you think about, how do I regulate turning on and off? And I'll give you a simple example. We have a customer we're working with that runs a cattle auction, and they have the cameras running all the time, but the auctions only happen, in each facility like a few times a week, right? So then the question is like, well, where do we figure out how to turn on and off the cameras? Because we don't want to look at all the data, especially if nothing interesting is happening. Well, you don't need to know that there's cows in the frame, right, in order to know that there might be something interesting going on. So, okay, maybe the first thing is we look for that there's an outlier lighting change on the frame, right? Well, that's algorithmically quite simple and something we can put at the edge without a GPU. And then if that happens, then maybe there's a second step, which is a simple image classification model that can not run optimally without a GPU, but can run without a GPU. And you can then say, okay, that's enough data for me to start the camera stream and then feed that to the cloud and let it do its thing from there. And then, we can do other things like frame deduplication. But we can also use tools, general purpose tools like SAM2, Segment Anything. I know that you guys have, we're one of the first ones to integrate into your product. We use SAM2 for segmentation and then generate polygons that we can use for regions of interest that we can send to frames on the edge. But the idea that we have, a simple motion or light change detection at the edge then triggers this cloud streaming, that right off the bat is a significant reduction in those types of use cases where there's not as much activity as there is raw data.
Yeah, it seems like there's not a big false positive problem, but there's a big false negative problem. So if you turn the camera on and it's not interesting, then okay, you're getting some extra frames. But if you miss the cow auction, then you miss the whole the whole reason why the camera was there in the first place. How do you protect against those types of mistakes from happening? How do you validate a system like that, which is maybe a little bit off the beaten path from kind of the traditional supervised training methodologies?
Yeah, I think you're right that the false negative versus false positive question is one that I've seen with a number of different use cases. This is the way I think about these vision systems. I think for the foreseeable future is not to replace humans, but to augment them and provide this extra layer of protection. So conceptually, the way I think about this is that these systems should not be the system of record. It's almost like a secondary system. Primarily, there's people involved that are going to be responsible for these things. And we might have it even as a fail-safe where we say, look, in this auction example, right, there should be a schedule with the auctions, and there's a person who can press a button to override, and there's different things that can be done as additional signal. Another thing we do quite a bit is batch processing of events that have already happened. That works well, especially for things like drones or other places where you're not going to stream the video live and you have to do batch. What I've found so far is we're kind of augmenting, and if you have that attitude, then it doesn't hurt you as much if you do miss something important, and if you've got some other safeguards in place, for sure.
One of the super exciting things about your business is, as you mentioned earlier, is that you're not verticalized and you're generally kind of vertical agnostic, and so you see a lot of different use cases and a lot of different ways that people are actually employing computer vision in the real world. I'm curious of some interesting use cases or fun problems that you guys are solving.
We have what we call our Plainsight Services Network, Vision Services Network, which is professional services companies that are using our tools as building blocks for creating solutions for end customers. And what's cool about that is then they're combining it with ERP systems, with cloud computing, with, in some cases, generative AI chatbots and creating agents and things like that built on top of this. And we become a small part of the solution. One customer we work with closely is a company called ThinkIQ, which is a manufacturing solution. And their primary business is collecting manufacturing data from up and down the supply chain. And they collect data from PLC systems and sensors and other ERP systems and also vision. And so that idea of combining this data with these other things, and then it can be used for everything from for their end customers like food manufacturing or tractors or defibrillator injection molding. There's so many different manufacturing use cases that have a little bit of vision in them. So that's one area that's really interesting, is that combination. Can't share too much, but I am working with a law enforcement group that, originally they were like, oh, let's try and connect this to all the cameras in our city. And what we found was that this goes back to this whole live camera versus batch thing. Well, it turns out they actually have a lot of data for cold cases, and they want to go back and look at their archives and figure out how they can, draw some better conclusions from that. And the other option is you have a bunch of detectives watching a lot of tape, and that's not really a great solution. So the question is, can we speed that up? And then I would say the other one we've seen quite a bit recently is related to queuing. So think about people standing in line or cars in line for whether it's a ferry terminal or drive-through. This has come up quite a lot as a business use case. And I did talk about cattle before, but I would say livestock seems to be one of our most interesting growth opportunities.
Right.
So that's our services partners can build up IP related to models that they can use for different training techniques. They can really use our tool set as the deployment, and they can build a business on top of Plainsight, which is my goal. I want to make it so that our ecosystem is making an order of magnitude more money than we are, where we can really provide this scalable software infrastructure and cloud infrastructure, and the solution providers that get our vision stack, they can use that for building really compelling businesses in different verticals without the upfront investment of hiring a huge army of computer vision engineers.
Yeah. So counting animals might be a tedious job. It's definitely a job that my daughter would love.
Yes.
And you guys are also doing a lot of counting of strawberries or agricultural items as well. There's a lot of counting just to be done in the world, which computer vision tends to be quite effective at.
That's right. That's right.
And so I wanted to get to the other kind of innovation piece here, which it sounds like you guys have thought quite a lot about, which is the right abstractions for this type of system.
Yes.
And how do you think about, in as much as you can share, what the primitives should be for AI and computer vision, and how to make these scale agnostic systems that are also vertical agnostic? Curious to hear your guys' thoughts on that.
Yeah, I happy to share. We have this one abstraction that we are quite proud of, which we call a filter. And a filter is drew inspiration from sort of Instagram filters, which you think about it's a consumer context, it's a social media context. But if you think about a filter in a social media context, you have a video stream and you swipe through these different filters that, modify your video in some way, right? They give you dog ears or make you beautiful or, turn your hair on fire or whatever it is, right? But it's really, you can almost think of it like an app store of computer vision apps. And there's a whole framework that Meta has built for app developers to create filters. And there's it's sort of a beautiful abstraction, but it really ties together two fundamental ideas, maybe three ideas, but the two of it is model and code together as a single unit, right? It's not just a model. And we talked about models are really derived from data. The model kind of just sits there, right? It has to be invoked. So you have to get your inference from it, and then you have to decide what the meaning of that inference is. Now that could be as simple as getting XY coordinates of a bounding box, but it probably in a business context could be more than that. So that's the first idea, is that model and code are intimately entwined, right? And so to build a computer vision app, you really need the ability to bring both those things together, strongly version it, make it compatible, and make that a kind of a singular unit. And then the second part of the filter is that if you really just think about video in and data out, you can create a pipeline that chains together filters. And so if you think about input, or we have these sort of source filters, and then there's these processing filters. We have utilities that don't even have AI in them. They're just literally just reusable, algorithms, scaling and cropping and brightening and that kind of stuff, all configurable. And then you have this output, which at the end could be putting data into SAP, or could be putting data into Kafka, or putting data into a JSON output or some other data format, right? And so you can build these chains. And we've used container technology, Docker containers, as the underlying runtime packaging format for it. So it's very friendly to cloud computing and runs anywhere that Linux runs, essentially. So now what you have is the ability to take discrete steps in a computer vision app, decompose it into a library of these filters that are really computer vision apps that have been packaged and follow specific inputs and outputs. You can chain them together, and you can now deploy them and run them in a variety of places. If you want to run it at the edge, great. If you want to run it in the cloud, great. If you want to run it as a serving workload versus a batch workload versus something you scale up on demand or whatever, you now have this library that's reusable. And because it's also strongly versioned and tied to models, you end up with a model version that is very strongly and very much tied to the filter code that will work with that. So now we can take my data, it becomes a model. That model is now connected to this. Now I have a very strong app packaging concept, and now I have the ability to reference and deploy it. That composition concept to me is really why this is so valuable. You can't really do that if you're just thinking about it in terms of I have models over here and I have some logic over there. You really need this abstraction. And what we found is that by taking this approach, all of a sudden you can very simply describe in a declarative way the specification of what this computer vision pipeline will look like. That's a huge amount of toil off the plate of the computer vision developer or data scientist. they don't have to think about that anymore, right? What they're thinking about is, do I have the systems in place to solve the business problem in front of me? And then getting that deployed, tested, and getting all the metrics around it.
Interesting. And is this fundamentally for technical users that might not have the ML capability, or is this also something which can be run by fundamentally non-technical users that can kind of compose these things, and they try to understand what the end business objective is, but might not have all of the kind of software and DevOps capabilities?
Okay, if I can dare to dream for a second, okay, this is what I imagine is all low code goes to agents in the future. And what I really think will happen is if we figure out how the fundamental infrastructure is well described and can be well kind of defined and manipulated and orchestrated, similar to what we see with Kubernetes and cloud and these other systems. If we get that base layer right, then we can move up the layer to the prompt layer. Okay, and I think this is what's emerging in. I mean, we see it everywhere, right? Whether it's code generated from LLMs or agent systems. I think the future, what it's going to look like is that you will interact at a layer that's prompts, but it will generate the infrastructure as code, for lack of a better term, right? It's kind of like infrastructure as prompt, infrastructure as code, and that will become the well-versioned artifacts that are operated on by these computer systems. So that interface can become an LM. So I think the mental shift I've gone is like, okay, instead of asking ChatGPT or equivalent, what do you see in this scene? What you're really going to end up doing is saying, ChatGPT, write me a program that durably can find the information I care about in the scene using these prompts and these parameters, et cetera, and have that generate essentially the Plainsight config, for lack of a better term, right? And now if you kind of go one step further, instead of it being a human that's sort of creating prompts on the fly, now imagine that the agents are being instructed from higher level prompts that are then deriving these kind of subtasks and other jobs. And now there's events coming in from the cameras. Where those events are defined comes from data and the business problem that is being described at the prompt layer. But that's kind of how I imagine we move this to the less technical users.
Right.
Is really by adding that really well-defined infrastructure layer that the humans can interact with at the prompt layer. That's what I think will happen.
So the prompt will be the fundamental human user interface in this scene.
It seems like it, doesn't it? I don't know.
My co-founder was talking to an investor, and he told them that a pixel or an image can be a prompt, and the investor's mind was blown. What does a pixel prompt or like an image prompt actually feel like in this context?
Yeah, it's a great question. Pixel prompt is something that we talk about all the time, and it goes back to this idea that like our streams of video are just pixels. And so the question is, when a pixel changes, what does it mean? And that's that compression question. So now, can we attach meaning to a pixel changing? Well, first step is like, can we define a task and then reduce that task to a change in a pixel's color value? So if you think about it in the instruction, right? We talked about taking video and compressing it down to much less data. Well, you can go the other direction and say, can I take a task and compress it down to the change in value of a pixel over time in a particular scene? Okay. If you can do that, then you can start to drive. Okay. So I've got a truck unloader agent. Okay, its job is to, when a truck comes and unloads the pallet, it goes and says, put it on this shelf over here in the warehouse. Okay, simple agent. You can describe in a prompt. But when the agent sees that a truck is unloaded, right, going back to some of these techniques, it can say, oh, I know the camera, I know a truck's coming, I have the schedule, I'm going to define a pixel prompt for the unload area of this warehouse. And then that's going to trigger the next step in the process, right? I see that pixel changed its color value, therefore that's going to prompt me to do something. And I can see what the business task is as an agent. And then it's going to say, well, I need to find space in the shelf. I look at my inventory system. I go, oh, shelf, F23 is available. Let's go put this, tell the human or robotic forklift to like take this thing there, right? And it's going to say, well, I need to make sure that this thing gets delivered and that my database is accurate. So do I have eyes on that shelf, right? Now I go look up in my database of camera feeds and I see, oh, I actually do have a live camera for that. So I'm going to go to that camera. Now, should the GPU and the agent be watching that camera 24/7? As discussed earlier, of course not. It shouldn't be watching that. It should say, I'm choosing to pay attention to this thing. So what is it going to do? Say, I'm going to say, I have eyes on this camera for that space, and I'm going to put a pixel prompt there. I'm going to create a segment around the space. and I'm going to wait for it to change. And when it changes, that's going to trigger an event for me to start paying attention again. That's kind of the agentic mode I think we'll get to with vision, because it really moves us from this chat-based concept to interacting with the real world. And the challenge with what I just described, to be honest, is that in its most brute form, it's incredibly expensive to do what I just, just purely from a compute perspective. If you start from the top, you say, hey, let's build an agent demo. The agent demo will be awesome. But then when you actually go roll it out, what will happen is it'll say, oh, well, now we got to spend $500,000 per facility on GPUs and no one will pay for it. So,
yeah, no, that's super exciting. I love it. It's like the combination of the thinking big, but also the pragmatism to actually get there. No, that's super cool. It sounds like you guys are solving a lot of like really relevant, useful problems to actually make these things work in the real world. I wanted to round out today just with a few quick fire questions, and I think you might have answered some of these in some of the discussion that we've had. But
Sure.
I'll start with what advancement in AI are you the most excited about now?
Advancement I'm most excited about is realism. Realism is the word I would use to describe it. I think that we've gone through an incredible hype, and we're kind of entering into a phase where you can start to separate the hype from the reality. And to me, that is the most exciting development. Leave aside any of the technical innovations. The technical innovations are amazing all the time. But what I would want to see personally as an entrepreneur and a technologist, et cetera, as a human, I want to see that this stuff finds its place into practical use that generates value for people and businesses. And if we can do that, then I'm going to be happy.
Cool. Yeah, let's hope it does. If you were to debunk one myth about AI, what would it be?
It doesn't have feelings. Do people think it has feelings? I don't know, but
I think some people think it has feelings. Yeah,
I think people think it has feelings, and I still cringe at any of those kinds of notions. I mean, it really is just data processing. We can argue whether humans are just data processors as well, but the AI really truly is just data. Yeah.
Yeah, we'll avoid going into that long philosophical debate. I'm sure we could discuss it for a long time. And that brings to the last question. What does AGI mean to you?
I think there's a practical matter, which is when you'll be able to trust AI at the level you would trust an assistant is probably a pretty good practical thing that's going to drive a lot of adoption. But I do think that we run the risk in a weird way of creating the dystopia of AGI that people predict without actually achieving AGI, because I think people are running after giving AI power, and power is the larger risk, I think, than intelligence in some ways, right? It's a tool that has to be in service of human operators. As soon as you move away from that mindset, I think you run into risk. And the first, I think, real world thing where this is happening is in self-driving cars, which have made incredible advancements. It's probably going to have the feeling soon that this is truly kind of an AGI level system. I mean, people already have it. People really enjoy driving around in LA in self-driving cars. But the power is what brings the risk. And so when you give the AI the control of those systems, that's where I think we really have to be careful.
Well, that's a great point, that the power and intelligence aren't necessarily perfectly correlated, and we can have maybe not generally intelligent systems that are still almost seemingly all powerful systems. Thank you, Kit, for the conversation. I really enjoyed it. It sounds like you guys are working on some super interesting problems in computer vision, and look forward to the next conversation.
Thanks, Eric. Take care.
Thanks. Have a good one.